I'm Mike Borza from Synopsys. I'm a principal security technologist with the Security IP group of Synopsys. And with me today are Ambar Sarkar from NVIDIA and Adam Sherer from Cadence. And Brent Sherman is with us in spirit, but he was the first guy to get a notice that he couldn't attend anything that involved large groups of people gathering together. And so Brent, although he prepared a lot of the material and is the chairman of the work group, can't be with us today, but he is with us in spirit. So just by way of introduction and the fact that you're here today, I suggest you already know this, but I'll just kind of lay the groundwork here a little bit. If you look at security risk, it's growing everywhere. If you look at the number of reported instances captured in the CVE database, which is really a software and systems database of security concerns or security issues or actual attacks, the numbers have skyrocketed in the past few years. Cybercrime economy is flourishing. There have been a huge number of increase in high-level security breaches in 2019, the year just finished. And actually, one of the things that's interesting is the number of inexpensive hacking toolkits that are appearing on the market. A lot of these involving both hardware and software. They range anywhere from, Brent has $1 to $200. I would say $0 because there are also a huge number of open source software hacking toolkits that are incredibly useful for both white hat and black hat hacking. And you see this all over the security industry in general, is that anything that's useful to us as engineers interested in providing secure solutions, it's also of use to people who would break down those barriers that we try and put in their way. And ransomware has emerged as a very popular attack, and it turns out to be running at about one new ransom notice sent out every 14 seconds, which is a kind of interesting statistic. So part of this problem is contributed by the fact that everything now is being connected. You've got peer-to-peer devices, you've got tons of small devices that are present, you've got devices talking to clouds, you've got clouds talking to clouds. We've seen the emergence of platform as a service and software as a service business models, and that's putting a lot of software in the cloud where it wasn't before, and a lot of the attack surface of corporate data and of private personal data is now in the cloud, meaning somebody else's data center. You've got multiple dependencies and assumptions that are built into all of this, both functional assurance kinds of concerns, and breaking the chain in one place causes it to fall apart. So you see denial of service attacks and botnet attacks. Escalation of privilege is still rampant. Information leakage, once you can escalate privilege, is rampant. Sometimes you can get the information to leak without having to escalate any privilege at all. And then you've got all kinds of code execution attacks for processor-based systems. The other thing that has emerged in the past 10 years is that you're seeing far more third-party IP and far more IP reuse within the chip design community. And this is large part because we've got massive chips now. People can't, and even companies often can't, fill up the whole chip with their own IP. They simply don't have the wherewithal to develop it all and maintain it all themselves anymore. Even things that we think of as simple interfaces are now extremely complex interfaces. So things like PCIe, USB even, these are getting to be very complex protocols. So you've got increasing demands for IP subsystems, for reuse, and for third-party IP, and these all lead to different kinds of security concerns. You have more complexity. With more complexity comes an increased risk that something is not secure. With that increased risk comes the higher probability that you're going to see attacks. Reuse means that you've got increased exposure. So you've got now the possibility of attacking one chip, learning something about a particular subsystem that has a vulnerability or a serious weakness, and you can apply that knowledge in the other places this is being used. And then you've got third parties, which increase the number of unknowns in the system. And so you've got third-party IP, which is generally treated as black box IP by the integrators, which becomes an unknown risk to those integrators and to their products. So just by way of showing you where we fit into the organization, of course, we've got the board of directors with whom you're familiar of Accellera. Within the technical committee, we have a large number of working groups, multi-language groups, the System Verilog, the analog and mixed signal teams, UVM and portable stimulus, IP exact, IP security assurance, and now functional safety is emerging roughly at the same position as IP security assurance is in the organization. And then we have all of the standards on System C, System C AMS, synthesis standard for System C, and System C verification. A lot of Accellera's work has fed into the standardization by the IEEE of various products, and so that is a path that we expect to see exploited for some of the work that we're doing here. So the IP Security Assurance Work Group was founded in October 18. We have 61 members representing 21 companies. All of the big CAD companies are represented here. All of the big IP providers are presented here, and most of the biggest chip companies in the world, as well as a few systems companies are represented. And we've had recent participation from the University of Maryland, which has a reason to want to get involved in IP security assurance. So the work group's agenda the scope has been to look at security concerns associated with integrating hardware IP into embedded systems. The concern is people don't know what exactly is being integrated when they get third-party IP. They don't know what the risks are associated with it. And they'd like to verify the completeness, accuracy, and overall quality of the supplier's products. And this is one way or one tool to be able to do that. So we looked at what existing standards are available that we can augment to incorporate security into the design process and carry that from design through verification. And the other focus is to look at what security concerns we as an industry-wide organization are able to know and understand about the products that we've built. The idea is to try to disseminate the knowledge about what is it that attackers successfully exploit? What are the common vulnerabilities that come from those kinds of things? And then can we adopt ways to mitigate that and spread that knowledge around so that collectively as an industry, we're making more secure products on the whole. Specifically out of scope in our work group's work has been the subject of how trust gets established between the stakeholders. In other words, between the IP vendors, between the EPA vendors, and the IP integrators who would use all the tools and the IP. That's not to say that's not important, but it's not something that we're going to tackle in our work group. And then establishing trust throughout the supply chain is also not in our scope. So if you look at some of the academic work that's been done on Trojan circuit insertions, things like that, we're not trying to solve that problem with this standard.
A little bit about myself. I've been in the functional verification industry for about 20 years. I was deeply involved when EVM came out, methodology. I realized I was involved in UCIS coverage. So since then, I'm currently at NVIDIA as a platform architect, focusing on internal hardware-related infrastructure. So given that, the way I take out of it is that here's this IP, there is a known set of concerns, and this IP you're getting, how does the developer know what is out there? Have they captured all aspects of it? And when you as an IP integrator get it, how complete is that information? How accurate is it? How do you check that? So this is really the part of the methodology that this standard is actually trying to promote. And to that effect, around September 4th, we delivered the first cut for consideration. And it talks about the methodology. It talks about the known concerns, the weaknesses that are known, that if your IP has any relationship with that, you should know about them. And then we sort of took an open course example because nobody is going to complain about, hey, you're taking my IP and showing it has weaknesses. And it's out there, open core examples. But they're really good examples to sort of explain the methodology. And then essentially, there's a summary and outlook of it. So it's a lot of material in that standard, and I'm going to go through each and every line of that standard in gory detail now. So I'm just trying to sort of give you an idea of what this standard is all about. I want you to connect at intuitive level so that you can go and get in and get more out of the standard, and hopefully we can enjoy your participation. So I'm going to only cover the methodology and give you an idea of where you get this common database, and Mike, you will be able to elaborate that a little bit more. And what happened since September, we have been going out and soliciting a lot of feedback. As a result of that feedback, we have captured a lot of this in an addendum that has been added on top of it. So we are really actively seeking input. So given the mixed background, I think it was good to sort of talk about a little bit of definition of terms, just to sort of set the ground. The asset is essentially what you're trying to protect. And in our case, because we are looking at an RTL kind of scenario, we are looking at essentially what is it within your IP boundary that you're trying to protect. It could be a counter, for example, or it could be bigger blocks than that. And then the threat is essentially anything that can attack that, but just because it attacked may not matter, so the concern is what is the consequence. And then the attack surface is how we are going to sort of enact that threat, all right? That's the attack surface. And there's also this notion of threat modeling, and all of you know this. I'm just sort of making sure getting the definitions in front of you a little bit. These are all standard definitions. So this picture is showing what changes in this flow of security. So the key idea is these gray portions are essentially what happens today. You have your IP standard that comes up with a definition, then your EDA tool does all kinds of analysis, etc., and then you sort of do simulation, formal verification, whatever. In case of formal, you will probably also use the EDA tool. But at the end of the day, that's the flow. So what we are doing is augmenting the existing flow. So essentially, what are the assets in your IP that need protection? That's fed into the IP definition. Okay, because you have to identify in your whole thing, not everything is vulnerable. There are certain aspects that are more important. So that gets into the IP definition. Then, and I will go over a little bit more, the EDA tools then look at this asset definition in the IP, and separately, there's this database of known security concerns associated with this IP family, and you will see that picture again. So the tool sort of takes this IP definition, and this asset definition probably has some kind of relationship, tells, okay, this asset or this IP has this vulnerability, so it takes all that into account, goes to the tool, and the tool says, okay, looks like these are the input-output ports that can let you enact a threat. And these input-output ports plus certain set of conditions and the kind of security you're worried about together is what comes out as a product of this. You as a security engineer, verification engineer, will use this to create your threat model and then go into this loop of verifying the security objectives. Now, security objectives, what are they? CIA. This is a standard definition of confidentiality, integrity, and availability are the key ones. So again, this is just to show that we are not really radically changing the flow. We are not asking to do something else. And we'll try to sort of make the case that it flows well within this existing flow. So here's a little bit more. And again, there's a lot more detail to it, how precisely it's done, how exactly it's done, and that's in the paper. I encourage you to read it, but you should get the basic idea from here. So the asset essentially is identified with the RTL path from the boundary of the IP. That asset belongs to a family, like is it a test debug interface or what, a bus or something like that. And there's a label that uniquely identifies what specific asset this is. So when I said an asset ties to the IP definition, so the IP is going to say like a USB bus or a counter or a computer operating properly. So the asset in the COP will be something like the counter. Then this IP family sort of says that, hey, for these kind of IP families, we have a bunch of known weaknesses, right? So essentially, the security weakness is somewhere in a database out there that has an entry and a very specific reference number, and it has an IP family. So sort of this IP family is related to that IP family. So if you have a test debug IP family and there is another IP family that's called test debug, then you get it from there, all right? And then you sort of, the EDA tools go in there. So the idea is that the tool takes these two together, munges it, and creates a bunch of input and output port list that can lead to you having access to the asset that's being protected, all right? And that it can do through like generally automated analysis, because it can do reachability analysis or something like that to sort of say, how do I get to that asset? And there'll be other things. And then what happens is you've got the input ports and output ports, and then this reference number matches this guy, and this label matches this guy. So the idea is that for this particular asset, for this particular weakness, these are the ports that affect it. And so the tool can generate these things. So now, okay, great. Now I know how the ports, I can access them. Now what? These ports, you have to tie them with what kind of security objective you have, right? And based on that, you create an attack surface. And how exactly specify this attack surface? Essentially, you have to say that, okay, under these set of conditions, maybe you specify the conditions as a system verilog assertion. Sort of say this sequence is met on these ports, then this becomes a factor. So essentially, you take these ports, that can be almost automatically generated, but how do you actually create the attack surface? It's kind of not necessarily going to be an automated process because there's a lot more thought involved there. But you as an IP provider know about how this can happen. You know the kind of weakness. So you sort of say that, okay, I can touch my asset and harm it with this security objective in mind under these conditions. And that's what becomes your attack surface. Now with your input-output ports and your attack surface with given security objectives, you can do your threat modeling, which is saying that, okay, I want to threat model all the confidentiality aspect of things. So essentially look at the input-output ports plus the attack surface that's associated with confidentiality and run your tests, et cetera, and verify. So that's essentially the flow. And again, the flow has been kept deliberately straightforward. It should not be more complicated than it has to be. Let's step back a little bit and walk through what is an IP provider going to do. So IP provider is going to sort of say, okay, here are my ports that can get you to that thing, and here's the attack surface, all right? Then it sort of says, okay, the attack surface for confidentiality may not be the same as the attack surface for integrity, right? So essentially, the IP provider is going to give you a list based on the known security concerns that affects that IP and the IP family, is that these are the ports that will be used to create an attack surface. Here is the attack surface, and the details of the attack surface, there are more detail about what kind of condition goes into creating the attack surface. And so essentially, the IP provider says, for my IP, for these kind of security objectives, here are the attack surfaces. That's a delivery to you as an IP integrator who's going to take it. So this is the second step of the IP provider. And then this whole collateral gets to you who is going to take this IP and work with it. Okay, so what are the things that got sent from the IP provider? One is the IP definition, but it has the asset definition in it. So the idea is that all the assets that were important from a security perspective would have been part of the IP definition. So here's my IP, here are the assets that are mentioned. This security weakness is already out there, so IP provider is not going to do that. All they will have is essentially the association of which security weaknesses might be there, and then gives you this whole attack surface, all right? So, okay, so IP provider gives you the IP definition and the attack surface and the input-output ports, fine. So now it has come to the IP integrator, okay? So you got this IP integrator. Now here is the thing. So IP provider gives me all this stuff. How do I know it's complete, right? So one of the things you can do is, you know the IP, you know the family, you have the EDA guy working with you, right? So find out from the EDA guy's tool and your IP definition and the family, what are the input-output ports, all right? So you can run the same task, except independently of the IP guy, and sort of see, okay, what are the input-output ports you're getting? And you can immediately get a general idea of the quality of the IP, because wait a second, for this kind of IP, I should have gotten these kind of ports which are vulnerable. I can put my threat in, and maybe the IP integrator forgot a side channel. You know, side channel as a port. That should have been mentioned here, and because there is some reachability to your protected asset, and that was missed. The idea is, this is one quick and cheap way to check that the IP you got is complete enough or not. Did it do all the work? So they are not telling you, here my IP is open and it's vulnerable. They are saying that for my IP, I know these are the set of weaknesses, and here's the attack surface, test it for yourself, all those weaknesses have been handled. So it's essentially saying that for a certain family of IPs, you have known weaknesses, and here is my IP, tells you how you can test against those weaknesses. That's all the IP provider is giving you. And you as a verifier are trusting but verifying in the sense that, okay, you're telling me these are the set of weaknesses that I know your family has. You have given me these attack surfaces to attack with. I'm going to test it. And I'm going to find out, okay, your family, what are the weaknesses? Let me find out and run my threat modeling and make sure IP is secure or not. Another aspect to think about is that you are looking at the product level. Like IP, as being an, by definition, IP has to cover a lot of ground. But you as an integrator may only care about a subset of it. So the IP provider will be a big list, and so think of it as a IP level collateral that they provide, but the IP threat attack surface could be large, but your product level consideration may be a subset of that, or you may have more of it. So you have to provide a mechanism to sort of define your own threats as well. And there is an approach to that I'll quickly get to. So here the idea is that two things. One is that you make sure your input-output ports have been covered, because if you're missing something, that means the IP doesn't have the quality. The other thing is you'll also get a set of IP attack surface definitions, and that you have to do some level of audit, because that's not an automated thing you could do. But you should look at it and sort of say, okay, these are known concerns. I'm getting the IP. Have I got all the attack surface that I expected to get? So there will be that aspect of it which I don't think you can get away from. So essentially, first thing is you take the IP, you sort of say, okay, given the concerns of this IP, which are relevant to me from my security objective perspective, and you only get those, and the rest you may not care about. So for example, if there's a debug port leaked some information, you might have decided at the product level, you're going to turn that debug port off. Therefore, any of the concerns that are associated with the debug port may not matter to you at all. So therefore, you will pick and choose the things that matter to you. Essentially, this is what I just said here, which is essentially pick and choose which ones you want, and those are in the scope of your product. And then you develop your threat model and make sure that's fine. The next question comes in, now that IP is in a bigger context, okay, you can essentially add more of your concerns and attack surfaces to on top of that. So you have a product level threat model that you can play with. So in principle, all we got essentially was a very simple flow, right? You sort of say, this is the security objective, this is the IP family, and based on that, the IP provider gave you a bunch of ports and attack surfaces. You got that. You sort of made sure, hey, did you get the same set of ports and attack surfaces that you care about? Great. You do your additional concerns you have, you put that on, and now you do your threat modeling, all set. So that was the overall flow, and again, there's a lot more detail to it, how exactly you specify your conditions and attack surface. That's in the paper as well. So the next thing comes in is that, as an example, this is common weakness enumeration that's maintained by MITRE. And if you're in this industry, you know that that has been on for a while, but it was mostly focused on software. So recently, some of the hardware-oriented design weaknesses have been added to the database, and that work is ongoing. So essentially, we are in touch with them, and we are working to see what comes out, but the IPSA standard by itself, as long as this information can be translated into the form IPSA wants, which is JSON or IPExact format that we are working on, we got there. So, and of course, CW is looking for the collaborations. If you have some weaknesses that you want to contribute, feel free to do so. The information is there. So to summarize, at least on the whole methodology part of it, it has to be fairly low and should not make you do a lot of changes. It's not messing around with your RTL design. It's outside the RTL. Simple technologies like JSON or XML should be able to specify those. And tooling should be fairly minimal. As you can see, it allows you to grow. It can select which ones you care about and add additional weaknesses on top to worry about, attack surface to worry about. And you can get some degree of automated generation of input-output ports and make sure you can check that you are getting all the right ports out of it. We have been collecting a lot of information since September. So we are planning to sort of do by May 20, we'll have the addendum, but I think we may have an earlier version out before that, and we'll, of course, actively solicit input. I really recommend you go to the forum. We hope to get a lot of discussion out there. There's not enough discussion. We want some of your thoughts in there. And at that timeframe around June, we hope to have a demo with the security weakness database, and then the public review is scheduled towards the end of the year. Here are all the information. So the key thing I would point out is this is the main page, Accellera, but this page is where you can sort of contribute. I have any questions, any doubt, any discussion, please feel free there. And some of us, all of us will jump in. We'd like to hear from you. And as far as you're talking about the database, you can look up here and can see all kinds of guidelines out there.
So I wanted to discuss a little bit more about the idea of capturing security concerns knowledge in the standard and how we intend to do it. Just to give you a bit of overview here, I don't want to go back and rehash everything, but we wanted to devise a way for the standard treatment of security concerns in IP. And as part of this presentation, I'll talk about our latest view on that and some of the underlying assumptions. So what information do we expect a useful knowledge base to provide? And then I've also got a view on how we expect this knowledge will be used by the CAD tool vendors. And since I straddle, both sides of that fence, I'm not a bad person to talk about that and think about it a little bit. So, of course, we are developing the standard for IP providers to communicate with IP consumers what the security aspects of particular IP products are. And So, it kind of serves two useful purposes that we explicitly stated. First is this informing the consumers of what the unmitigated concerns are in a particular IP, and they can decide whether they care about those concerns or not. In some cases, people won't care. In other cases, people will care. And then it allows the objective comparison of security properties of different products. So they may have the same functional specification. You've got two PCIe interfaces from two different companies. Do they have similar kinds of IP security concerns? There wasn't a widely available catalog of known concerns that pertain to hardware at the time that we started this work. And so that led to our creation of the known security concerns subgroup, which is focused on this. And our plan is to capture this knowledge in a common IP security concerns enumeration. You can guess by that name, aside from it being long and a bunch of letters that don't make a particularly nice acronym. If we'd been clever, we would have done something that made a cute word, but I guess that's probably my fault more than anybody else's. But we looked at what the CWE did for software and, as I said, to a lesser extent for systems. And we also looked at CVE, the Common Vulnerability Enumeration, which is specific vulnerabilities that relate to software. And in that database, you find much more information about both specific concerns and how to trigger them, how they can be mitigated, and what kinds of information leak or are destroyed by the particular vulnerability. And then you also find that there's a lot more system-focused concerns that are captured in that enumeration, and even a fair number of hardware concerns are captured in that enumeration, or things that are fundamentally traceable to the hardware. So as we progressed our work in KSC, we started to develop a prototype of the CPC database. We used a common tool called Sherer, which is kind of like a wiki on steroids, or a cross between a wiki and a Bugzilla, let's say. And we also learned that MITRE was interested in extending their CWE database to include hardware. And so that got us talking together to see what we could do. And at this point, I'll say we're still talking together to see what we can do. So it's not at all clear that we're going to produce one product that is the merger of the two things, or what we're going to do about that. Everybody in the work group was polled. We all have different positions about what we should do. And, we're still trying to figure that out. So that's just being blunt and honest with you. To accommodate the possibility that the security concerns knowledge bases will not merge, we looked for the sort of minimal subset of information that needed to be common to those, at least the CWE and the CPC database, to make them some way interoperate with tools that we imagine will be built. And what it finally came down to was one attribute, which is essentially the family attribute that we can attach to a concern and say, okay, this family of IP tends to see repeated exploitation of defects of this type, and so these are the things to watch for. And so using that family value in the IP description, the product description, and then in the weakness enumeration, we can connect these two things. Now, it's simplistic to say that a single family captures the sentiments or the issues for all possible weaknesses and for all possible IPs, and so it's allowed for a particular entity to have multiple family members ascribed to it. So the 16 that we have on the list right now is the list I've shown here. It's gone up and down as high as 20 at sometimes, and we've kind of merged things and combined them back down. But critically, there's a user-defined category which allows us to capture things. I would argue that we don't capture I/O on chips very well in this. There are too many places where you could ascribe that or assign those kinds of products to. And so that's, I think a little bit of a deficiency in our list right now, and we'll see whether or not we should extend that a little bit. But once we had the family, then, that's the main thing we need in order to be able to relate things. But that leads to the bigger question, what knowledge do we need to capture and what information do we need to capture in order to produce something that is fairly complete and useful to people trying to analyze security properties of their products. And so the information is similar regardless of what the field names in a database you might ascribe to those are. In general, any useful database or any useful encapsulation of this knowledge is going to have some kind of reference identifier. that's unique to the particular entry. So that's just, usually an alphanumeric handle on which to hang the thing. In CWE, they identify it as CWE dash, and then a 4-digit number or 5-digit number. There's a version identifier if you're allowed to have multiple versions of an entry. So maybe somebody wants to capture the information and show it as a point in time, and then be able to evolve that information as you learn more about it. It makes sense to associate a version identifier that's also unique to that particular reference ID. A title, you need to have a name to look for, some kind of problem that you can tell people about. Description is a detailed overview of the concern. Relationship, which is just cross-references to other concerns. So the obvious thing is to use the reference ID of the concern in a different database. And there's no reason that different databases can't refer to information in other databases. So the CPSI database can refer to entries in the CWE database, and CWE database can conceivably refer to entries in the CPSI database. And then examples obviously seem like a useful thing to have in all the IP concerns that one would have, because it helps to show what the concern is and how it's exploited. Consequence. This is kind of the hard nugget of security. And it's really, telling the user what the nature of the concern is. So are you concerned about confidentiality? Are you concerned about integrity? Are you concerned about availability? I've given paraphrases here of the definitions we're using. And we really adopted the NIST FIPS 199 standard as our language source for the CIA. And I restated this slightly to put it into a more positive description than the way it's described in FIPS 199. So that's why I say I paraphrased it. But I hope I didn't do too much misjustice to it. So applicability is the family or families of IP to which the concern corresponds. And we can have a wildcard, which probably will be something like all or star, because we're imaginative that way. So it's the only attribute that we require of the knowledge base in order to allow automated tools to connect concerns to potential weaknesses within IP or in the way that IP is being used. Modes of introduction. So this is, the life cycle stages at which we're concerned about these things being introduced. And it can be sort of any combination of these things. So you can have, introduction of problems during design or during architecture, during its implementation or in manufacturing and provisioning. And all of those are possibilities. So they may lead to more specific concerns that relate just to one aspect of this. And it won't surprise me if you see that. And you see this frequently if you look at the CWE database and how things get broken down. They often break things down into, a specific concern that's associated with implementation or a specific concern that's associated with the architecture phase. Similarly, mitigation is important because you can often think of ways to mitigate something in general so that you can avoid the problem altogether. You would hope that if somebody, plans to address a particular issue with their product, that they've used one of the mitigations that's available to them or several of them in order to mitigate that problem. So sometimes you can use clever architecture to mitigate a concern. One of the things that I like to come back to and emphasize is that it's not unexpected and it's not unreasonable for IP products to leave particular security concerns unmitigated. And this is the communication aspect of this standard, which is to state what issues are not being mitigated. The reasons for doing that are things like, you can imagine reasons for doing it, but a lot of times it's more appropriate to handle a security concern or the mitigation of it at the system level or at a higher layer, a subsystem level, so that you close off a whole family of unmitigated weaknesses that are related in a single solution. And so a good example of that is sensitive registers in different IP cores that are all being used inside the same subsystem. It makes sense to provide an access control, it may make sense to provide an access control mechanism at the subsystem level that then enables access to all of those things or to some subset of them. And so in that case, it's perfectly appropriate for the IP to leave it unmitigated and simply inform the consumer of the IP to say, okay, here's a concern. If you're worried about things that are going to attack your system by going and twiddling these registers, you need to close this off at your system level or subsystem level during integration. CPSI, we think, is going to be useful in its own right, just as a design reference, and CWE is useful in that same way, in my opinion. We expect that tool providers are going to incorporate the knowledge in CPSI and in related databases into automated analysis tools. And I know that there's work going on around the industry that's very, very early, but is trying to do some of that now. So I expect that what will happen is that the data will be imported into the tool, either because it's able to directly read what we produce as a standard for the CPSI information, or because there are translators that exist to translate between the different formats. And those could be put together fairly simply, we think. The collateral then includes the security attributes file that identifies the assets and then the concerns for each of the assets and whether the concern's mitigated or not. And then the tool is able to use that combined with the descriptions that come with the IP to produce an attack surface and possibly produce automatic analysis of the IP under those attack scenarios. And as it's integrated into a complete IC, you can see extending this up to higher and higher levels of abstraction so that you can actually prove out that you've started to close mitigations as you're integrating stuff together and building a kind of modular set of subsystems. So just to sum up, we think that CPSI is going to provide a decent standard for documenting, disclosing security concerns to designers and to people who would use those designs. Single attribute, the IP family, is what we need to be able to relate these things together between the known concerns and the IP families that are concerned about them. And then it's expected that tools are going to be able to inhale this information and use it to produce useful analysis to demonstrate that you're achieving certain IP concerns or in closing them off, meeting the security objectives for a product.
So I'm going to take us through actually what we've actually uncovered in a lot of the conversation, which is taking a look at obligations or best practices in the space. Obligations is a bit aggressive in the statement. I kept it because it was part of what we wrote into the overview, but I really think it's best practices at this point or anticipating those. So we're talking about in process, so let's take a look at notes from the future. If we were coming back in a few years, what would we hope to say here? We want to thank the Safety Working Group because due to their fine work, we now have flying cars. They're secure because of the work that we all have done between the committee and you all using the standard, and it's in broad use. But this has actually been the subject of a number of your questions. How would we get there, right? We're establishing some standards work that Ambar and Mike had talked about, but what are some best practices when these things arrive? Just for slide convenience, I talk about IP suppliers, IPS, and IPI. We're not planning new acronyms. This is just a uncle, as we say on the East Coast. It was just a way for us to just make the slides a little more clear. But it's for trusted IP delivery and then maintaining that trust, right? This trust but verify, we've used it in context a few times here in the presentation. But if the IP provider is doing the work, there is an obligation on the integrator to maintain it. So we'll start off with general guidelines on what we expect in coding the IPSA tables. They should be in both a human and machine readable form, right? We talked about encrypting IP, protecting the intellectual property inside that design element. The description of what the attack surfaces are, the assets associated, the elements we carry in the tables, we're recommending as a working group to be machine readable and human readable, right? Because you want to have an expert opinion security lead examine this, but we also need it to be automated in the process. And so there's a machine readable aspect too. We're recommending JSON as a compact notation. We've been in discussions with the IP exec team as well. It's a way of coding it, but we believe it's not, even though it's clear source, it's not easily human readable because it's big. I think it's a technical description of an IP exec description. 2 engineers should code the tables as a check and balance. All right, so here, in a positive way, you have engineer A looking over engineer B's shoulder. Maybe they have a different perspective. They can find things that maybe someone has missed. And then, it's different disciplines, design and verification as an example, or test engineers. The implication of this statement is if one of the individuals happens to be less than trustworthy, there's a second set of eyes for that. All right, this is a concern in security space. If you have a single individual and that person is compromised in some way, they could be providing a description that is itself compromised. Formal techniques. I think this is something that a few of the members in the working group surfaced quite a bit, is that simulation, as exhaustive as it can be, will not cover all the state space. It cannot. Formal cannot necessarily as well. I'll come back on that when we talk on the integrator side. But wherever possible, the techniques should be used. One that we particularly talk about is identifying attack surfaces from assets. That is a made-for-formal application. Searching for unanticipated or unexpected assets. All right, again, another way of not calling out a Trojan intrusion here, but if you do have access to clear source, certainly as the IP provider, one of the things that you should do ahead of release is look and see, are there assets in this design that have not been identified? It could simply be oversight. All right, you could have a formal tool that looks for potential assets in that IP block, and it's just that the expert that was looking at it and developing the documentation didn't see it. Then there's a worst case that could come from that as well. And then trust but verify the tables against the IP. All right, so these are two different bodies of intellectual property, the source code for the design and the tables. They need to be verified together. So I mentioned documentation traceability. That should be part of any development environment, using formal engines to read it, and then gathering coverage and building up a model of what you have verified. So encrypted or not encrypted. If you encrypt the IP and the tables, you could lock down the interfaces, right? And there's some advantages in that. It limits the integrator's ability to circumvent your APIs, right? So you've defined the way that the IP should work. You've built a set of verification for that IP, and you're expecting the integrator to follow those rules. If you provide clear source, there's always a risk that the integrator, and I'll talk about this more, let's say just innocently says, oh, well, I don't need that API. There's a different way for me to access the information I need. Or the IP creator wasn't that smart, and this is a better way of using it, so I'll just fix this API a little bit so it's faster or more efficient. That has potentially unintended consequences. As the provider, you may want to encrypt it. You're going to need to provide a lot more data to substantiate the work that you've done. So that traceability that we mentioned before, you may be required by the consumer of your IP to demonstrate, what have you done? What is the completeness? Show me those formal reports to demonstrate that what you provided is complete enough and trustworthy. But in the end, the tables need to be machine readable as well. Or you can provide the complete source code, right? And that allows the integrator a straightforward path to do a trust but verify. That's assuming that the integrator actually understands the IP, can, interpret the results of doing their own verification, that trust goes both ways. But then there's the risk that new attack surfaces will be created because the IP integrator is fixing the IP. On the supplier side, this idea that tool confidence level at work, the description that's in the various industrial standards, I pulled it out of 26262 as a reference point, but 61508 and all the ones that derive from it, all the FDA ones, they're all very, very similar. And they're all about making sure that you have trust in the individual tools and that there's a known path for accepting new versions of tools, right? And that's what we really want to talk about here is that the IP and the tables need to remain current. We need to know that for newer versions of tools, the IP remains verified, right? And then that the IPSA tables are still current and working with the tool set. Create a concept of a security manual. Document what you've done, right? There are defined intended uses of APIs. You have a debug interface for the IP. Describe how that needs to be turned off or cauterized when you integrate to the system, as an example. Document the known errata, right? This is a scary part, but as an IP supplier, if there are bugs in the system, you're going to need to provide that information to the integrator. They need to know what the impact is in their system, right? And maintaining that's going to be critical. These things are generally true in safety concerns, and I think we're going to need to address them. And then you need to keep up with the tool versions. For some of the consumers of the IP, in some of the longer life cycle application areas, this is probably the hardest thing to do. All right, so if you're supplying IP into automotive, into defense, into aerospace, so you need to maintain currency, and that's probably one of the biggest challenges, I think, in the space. As the integrator, you got to know the IP. You can't just accept the data sheets and run with it. You need to spend time with the IP supplier, understand what they're actually supplying, set up expert reviews of all the documentation, both functional side and security side, to be aware. Conduct an API design review. Make sure that you're checking with the IP supplier. Am I integrating this properly? Is there anything that I've overlooked? And identify potential threats within your target system. Use an expert assessment by your own security folks. Trust but verify. So verify that the IP package is properly received. Communicate a checksum or some method by which you've assured a secure transmission of the IP. Right? There's always a risk that something happens in between, so you have to check for that. Verify the functionality and the security. Regenerate the tables. We talked about that earlier in the presentation. Use formal engines to validate that the tables are correct to the IP. Right? Again, make sure you received the information properly. Automate the validation of IP to known threat databases. Here I use the examples we mentioned, but I think one of the points Mike's making is individual companies have their own threat databases. Right? And some of these, they are very, very secure. Certainly in defense, there are security databases that we have no access to, nor should we. But there will always be secondary databases that we need to be concerned about. Make sure that you have an automation to those. And take action on anomalies. Set up that culture of security so that if you see something that's not right, you have an internal path to raise that issue, document it, and take an appropriate action. Right? And that could be as far as finding new suppliers. And then ongoing, always monitor the updates from your supplier. Right? They should have an errata path. You should be in tune with that with the full life cycle of your program. If it's prefab with the ASIC, implement it. If it's FPGA, you have an ongoing life cycle to maintain. Maintain the security analysis throughout the life cycle. Security doesn't stop when the FPGA or the ASIC go on a board and get shipped. Zero-day attacks can happen at any point. That's the definition of zero-day attacks. And new threats can arise as people continue to threaten. So this is a never-ending analysis. You can't assume that what you've done for the main project follows through for all the derivatives. You need to look at each individual derivative as its own separate project. And certainly true for new projects. Yes, you have knowledge, you have experience, you have infrastructure, but you have to assess the security at each individual project. And the bottom line is you just have to assume that new hardware risks are going to arise. All right, we talked about this in the threat database. Those threats can't ever come out of the database because if you drop the threat because, oh, it's been solved in every application, history will repeat itself. So the summary of security is and always will be changing. We have to establish that culture of security, and you have to stay current. Thank you.